Is this function one-to-one? Use the horizontal line test. So we're given this graph of a function, and we want to know, is this function a one-to-one function? So I pulled in from our notes here a definition of what one-to-one is. A function f is one-to-one if for any values of a not equal to b in the domain of f of a is not equal to f of b. So a and b are in the domain, so these are x's. So we've got two x's, and we've got the not equal to symbol there. So these x's are different. And then over here we have f of a and f of b. These are y values with a not equal to symbol, and the y's are different. So this definition of one-to-one is saying that if we have different x values, then we should also have different y values. And we can think of this as every y being unique. So we will never have a y value repeat. And then in the directions here, it says to use the horizontal line test. Now, I'm going to describe the horizontal line test for you in just a second, but we're going to first think about why we're going to use a horizontal line at all for this type of definition. So with a horizontal line, if you think about a horizontal line, like maybe this is at y equals 1, that horizontal line will have ordered pairs, and every single one of those ordered pairs would have a y coordinate of 1. And this is the opposite of what we're saying about y in terms of one-to-one functions. So instead of y being unique with this horizontal line, all the y's are the same. So this horizontal line is the opposite of a one-to-one function. It's most definitely not one-to-one. And so we use it as a comparison to our graph, and it helps us decide if a function is one-to-one, if a graph is one-to-one. So with the horizontal line test, what we do is we draw horizontal lines on the graph, and we're looking for the intersection points. And those intersection points, since there's only one of them, that means that there's only one of those y values. And if there's only one of those y values, we're going to be able to say that all of those y's are unique. They never repeat. So if a graph is going to pass the horizontal line test, it should only intersect the graph in one point. Exactly one point. Now the part that gets a little bit confusing with this graph is this part that I'm going to circle here. This part of the graph, it looks like the curve begins to turn into a horizontal line, which I just mentioned, the horizontal line is not one-to-one. It's what we use to compare to things that are one-to-one. However, that's not what is happening on this graph here. The graph does not go horizontal. You can see that right here the graph begins to curve, and it is very slowly getting closer and closer to a y value of 0. So if you could imagine for a second, if I were to zoom in on this portion of the graph, you can see that you have a curve that's going down like this. And if you did the horizontal line test on that portion of the curve, you would only intersect in one point. And then if you zoom in on this part of the curve, this is the part where it gets confusing because it looks like it's a horizontal line, but if you zoom in on that part, you're going to have your x-axis down here somewhere, and the curve, it looks really, really flat, but it's not. It keeps going down and down and down. So when you do the horizontal line test here, it's only going to intersect in a single point. And if you continue to zoom in here, that curve is getting, more and more flat, but it will continue to go down and down and down. It's going to continue to get closer to your x-axis, but it will never reach it. There will always be a little gap in between the curve and the x-axis. So these y values, they are unique and they never repeat each other. So this function is one-to-one. Is the function one-to-one? Yes, it is a one-to-one function. Give the rule that describes the piecewise defined function in the graph below. So in this graph, we can see that there are two pieces. We have a linear piece here and a constant piece here. And I want to write that piecewise defined function. So first of all, noticing that there are two different pieces of this graph is going to tell me what format our piecewise function will be in. So I know that because there are two pieces, there'll be two equations, and then there'll be conditions that go on those equations. So I like to start by finding the conditions first, and the conditions are going to involve the x's. So what I want to pay attention to is the x for which this line starts and the x where it ends. So this starts at an x of -9 and ends on an x of 2. So my x is going to be in between those two values, a -9 and a 2. So we're going to use less than symbols, but I also notice that the endpoints of that line are included in the line, so I want to include equal to's on my conditions. The other line is going to start at an x of 2, and we have this arrow, and that arrow indicates that it's going on forever to the right, meaning towards infinity. So for this one, the x is going to be greater than 2. And I notice that the end of the line has an open circle, so I am not going to put an equal to on that inequality. So I have the conditions for this piecewise function. Let me erase my lines. And I want to find the equation of the line. So let's start with this one here. I'll call this equation 1 and this one equation 2. Now we have multiple strategies for finding the equation of the line. So I'll show you two different strategies. So with the first equation, we know that it's a linear equation. And linear equations can be written in the form y equals mx plus b, where m is the slope and b is the y-intercept. So one strategy might be to notice that the y-intercept is right here, which is a 1. So b is 1. And then I could also find the slope of the line. Remember, slope is going to be rise over run. So on my graph, I would want to make sure that I'm picking 2 points that are lying right on the intersection of this vertical and horizontal line. And it looks like I have a lot of these, so maybe I could pick this one and this one. And I noticed that I would rise 1 and run 1. So my slope is going to be 1 over 1, which is 1. So I could have the equation being 1x plus 1, or just x plus 1. So that first equation is x plus 1. So I promised you a second way to do it. A second way to do it would be to maybe pick 2 obvious points on the line. So you've got this one labeled here as 2, 3, and this one here labeled as -9, -8. So I could take those 2 points, -9, -8, and 2, 3. I could let one of the points be x1, y1, the other be x2, y2, and I could calculate the slope. So that's 3 minus -8 over 2 minus -9, and we get 11 over 11, which is 1. So now we found the slope of the line, and I can choose one of the points along with my point slope form, y minus y1 equals m times x minus x1. That's y minus 3 equals 1 times x minus 2. And we have y minus 3 equals x minus 2. 1 times anything is itself. And we add 3, and we get y equals x plus 1. So you can see we got the same equation with a different method. Now the second equation is horizontal line. And horizontal lines always have an equation that is y equals the value of b, the y-intercept. And if we extend this line, you can see that the y-intercept would occur at 5. We also notice this point has a 5, and all of the ordered pairs on this line have a 5. So the equation of this line is y equals 5. And in our piecewise defined function, 5 is our second equation. So we found that the rule that describes this particular graph is x plus 1 if x is in between -9 and 2, inclusive, and 5 when x is greater than 2. On this example, we want to use the graph to evaluate the given expressions or state that it's undefined. So in our picture on the right-hand side, we have a line which is labeled as G, and we have a curve that is labeled as F. In part A, we want to find F plus G of 9. I'm going to follow the notation here, and this is F of 9 plus G of 9. So in our picture, we want to identify when we have an x value of 9. So I'm going to draw a vertical line here. And the reason why I'm drawing a vertical line is that all of the ordered pairs on this vertical line have an x of 9. And I'm noticing this intersection point here and this intersection point here are on the graph of f and g. So those ordered pairs are 4, 9, and, excuse me, I've got that backwards, 9, 4, 9, 4, and 9, 3. And f of 9 is equal to 3, and g of 9 is equal to 4, and we're going to add those together to get 7. So we found f plus g of 9 to equal 7. So this is subtraction. We want to do the same thing with subtraction. And this one has a negative 9 instead of a positive 9. So let's identify that on the graph. I'm drawing a vertical line at negative 9 because these are all the ordered pairs that have an x of negative 9. We've got two intersection points, and those intersection points are negative 9 and 3, and negative 9 and 2. This one in red is intersecting the graph of f, and this one in blue is intersecting the graph of g. So we want to find f minus g of negative 9. That's f of negative 9 minus g of negative 9. F of negative 9 is 3. And g of negative 9 is 2. 3 minus 2 is 1. So we found that f minus g of negative 9 is equal to 1. So in this example, it says g times g, and it's of 9. We've already marked 9 on our graph. We're going to do g of 9 times g of 9. And I'm going to go back over here and label this. The blue graph is g, so this point is on the graph of g. The red graph is f. So we want to use g. G of 9 is 4. And we have 4 times 4, which is 16. And our final problem here is f over g of 9. That's f of 9 over g of 9. We've already got 9 marked on the graph. F of 9 is 3 and g of 9 is 4. So we found f over g of 9 to be 3/4. On this question, we want to find f composed with g of x for the indicated functions and simplify. So the indicated functions are f of x equal to 8x plus 1 and g of x equal to 4 over x plus 1. So these symbols, f composed with g of x, this symbol here is an operation on functions, and that operation is substituting one of the functions inside of the other function. So what it means is that we're going to take the function that is in front of the composition symbol, that's our outside function, and the function behind the composition symbol, that's our inside function, and we're going to do that substitution. So for this example, we're substituting g of x, which is 4 over x plus 1, into f. And when we substitute it in for f, we put it in place of the variable, because what's inside the parentheses is our placeholder for that. So we're going to put in place of that x, 4 over x plus 1. That's going to give 8 times 4 over x plus 1 plus 1. And when we multiply here, we consider that 8 to be 8 over 1 times the fraction 4 over x plus 1. And we multiply those fractions together, and you multiply numerator times numerator and denominator times denominator. So this gives 32 over x plus 1 plus 1. Now we're going to take it a little bit further, and we're going to simplify this to be in a single fraction. So we have 32 over x plus 1 plus 1, and we treat 1 as 1 over 1. And to get a common denominator, we would multiply by the other denominator, x plus 1 over x plus 1. That gives 32 over x plus 1 plus x plus 1 over x plus 1. Now we have fractions with a common denominator. We can combine the numerators. That's 32 plus x plus 1. And 32 plus 1 is 33. So we have x plus 33 over x plus 1. So we were able to work out that f composed with g of x is equal to x plus 33 over x plus 1. On this question, we are given a graph of the line g of x and the curve, this is a parabola, f of x, and we have a few questions related to composition of functions. I'm going to give you these questions one at a time, and we'll work through them. So the first one we're going to work on is f composed with g of 1. Now this operation of composition is substituting one function inside of another function. So what that means, we're going to rewrite it with that idea in mind. F is our outside function and g is our inside function. And we're going to start on the inside by finding g of 1. So to find g of 1, I'm going to draw a vertical line at x equals 1. This shows me all of the ordered pairs that have an x of 1. And I notice this intersection point on the graph of g. That point is 1, 2 on the graph of g. So I know that g of 1 is 2. And then once I've simplified g of 1 to be 2, now the symbols that are left are f of 2. That 2 is an x value, and so I'm going to draw a vertical line at an x value of 2. These are all the ordered pairs that have an x of 2, and I'm interested in this one here that intersects the graph of f. And that ordered pair is 2, 0, and that is on f. So f of 2 is 0. So we have worked out that f composed with g of 1 is equal to 0. So let's try another one. The next one we're going to work on is g composed with f of 1. Once again, this is the operation of composition. Composition is substituting one function inside of another function. So this time, because g is listed first, g is our outside function and f is our inside function. So we're first going to find f of 1. And I've already drawn that vertical line at x equals 1. And here's the intersection point, and that point is 1, negative 1 on the graph of f. So f of 1 is negative 1. Then I want to find g of negative 1. I don't have that marked yet. Let me draw a vertical line when x is equal to negative 1. And I'm interested in the graph of g. So here I have an intersection point. So let's label that point. That's the point negative 1, 0 on the graph of g. And so g of negative 1 is equal to 0. We've got g composed with f of 1 is equal to 0. I have another one for us to try, and that is g composed with g of 0. So this is composition again, substituting one function inside of another function, and this time g is both the inside and the outside function. So we'll write that as g of 0. And on our graph, let's mark with an x of 0. And I've got, for the graph of g, an intersection point right here, and that's the point 0, 1. So g of 0 is 1. And now we have g of 1, which we already have marked right here. G of 1 is 2. So we found g composed with g of 1 to be 2. Let's try another one. On this one, we're going to work out f composed with f of 3. We don't have that one marked on our graph yet. I'm going to draw a vertical line at x equals 3. And I have an intersection point for f right here. That's the ordered pair 3, negative 1. And f composed with f of 3 will be f of 3. F of 3 is negative 1. And f of negative 1 is marked right here. Or no, I don't have it marked yet. Let me mark it. F of negative 1 is right here. Negative 1, 4. Excuse me, that's 0. I've got it wrong. I'm backing up there. Okay, here's where x is negative 1. That is negative 1 with a y of negative 9. F of negative 1 is negative 9. I've got 2 more to go, so I'm going to make some space here. And on this one, we have f composed with g composed with f of 2. So we're just going to nest these all together. This is composition again. F on the outside, then g, then f. So we're going to find f of 2 first. We already have that right here. F of 2 is 0. Then we're going to find g of 0. G of 0, we've already marked that. That's 1. g of 0 is 1, and then f of 1, we already have that marked right here, f of 1 is negative 1. And our final question is going to be g composed with f composed with g of 0. So this is g of f of g of 0. We'll start with g of 0. See, g of 0 right here. G of 0 is 1. We have g of f of 1. And f of 1 is right here, negative 1. And g of negative 1 is right here, which is 0. So we found g of f of g of 0 to be 0. An object is launched vertically in the air at 41.65 meters per second from a 4-meter tall platform. Using the projectile motion model, h of t equals negative 4.9 t squared plus v naught t plus h naught, where h of t is the height of the projectile, t seconds after its departure, v naught is the initial velocity in meters per second, and h naught is the initial height in meters. Determine how long it takes for the object to reach its maximum height and what is the maximum height. So in this example, we're given this function that you may or may not be familiar with. H of t equals negative 4.9 t squared plus v naught t plus h naught. And in this function, it gives us the height of the height of the object at a moment in time. So this h here represents height. This h here represents height, and this one here. Now, as it mentions in the description here, v naught is the initial velocity, and that's what's mentioned right here in the beginning of the problem. The object is launched vertically at 41.65 meters per second. That is the velocity. That is our v naught. So we're going to substitute that value in for the v naught here. And then it mentions here that h naught is the initial height in meters. And this object is launched from this 4-meter tall platform. So this is the value of h naught. So we're going to substitute those values into this formula to make it a complete equation. It's negative 4.9 t squared plus 41.65 t plus 4. So this function is going to give us the height of the object at every moment in time. Now, when we read the question more closely, it says determine how long it will take to reach the maximum height and what is that maximum height. So this word right here, maximum, within the problem, gives us a clue as to how to answer the question. So in this section, we're dealing with quadratic functions. And the graph of a quadratic function is going to be a parabola. Now in this particular example, the leading coefficient, A, is negative 4.9. The graph of a parabola with a negative leading coefficient is going to be a parabola that faces down. And remember, we're looking for the maximum height, and that maximum height is going to occur at the vertex. So we're going to be able to answer this question about how long it takes to reach the maximum height, as well as what the maximum height is, by calculating the vertex. Now, we can calculate the vertex with the vertex formula. The vertex formula contains an ordered pair, and we have a formula for the x-coordinate of the vertex, that's negative b over 2a, and the y-coordinate of the vertex. Although there is a formula for this, I never use it. I just substitute that value of negative b over 2a into the function to get the y value. I just want to point out one thing that can be a little bit confusing here, is that the vertex uses the letter h, and that h is different from the h that we wrote over on the other side. So remember, the h, which is the name of the function, is height, and the h over here in the formula is the x-coordinate of the vertex. So when we're finding the vertex, we're going to calculate h. This h is the x-coordinate of the vertex with the formula negative b over 2a. The b in this is 41.65, so we have negative 41.65 over 2 times a. A is negative 4.9. And let's get our calculators out so we can work this out. We have a negative 41.65 divided by, and I'm going to put parentheses around my denominator because there's more than one thing. I want to make sure the calculator knows what goes into the denominator. 2 times negative 4.9. And so we have 4.25. So in calculating the vertex, we got this 4.25 number. Now usually this is an x-coordinate, but if you'll notice in our equation, we don't use the variable x, we're using the variable t. So this represents t, which is a time, and time is given in seconds for this. So we found that the vertex is at 4.25 seconds. And that's going to be the time it takes to reach the maximum height. Now then, to find the maximum height, we're going to find the y part of our vertex. So I'm going to substitute in for the height function 4.25. Now remember, this h, this is for height. And we'll substitute that into our formula for height. I'm running out of space here, so let me write it down here. Negative 4.9 times 4.25 squared plus 41.65 times 4.25 plus 4. And let's bring back the calculator. We have negative 4.9 times 4.25 squared plus 41.65 times 4.25 plus 4. So we've got 92.50625. And so we're going to reach a maximum height, and let's round to one decimal place, 92.5 meters. Meters is the units used in the problem. We're going to reach a max height of 92.5 meters at t equals 4.25 seconds. A toy rocket is shot vertically in the air from an 8-foot tall launching pad with an initial velocity of 104 feet per second. Suppose the height of the rocket in feet t seconds after being launched can be modeled by the function h of t equals negative 16t squared plus v naught t plus h naught, where v naught is the initial velocity of the rocket and h naught is the initial height of the rocket. How long will it take for the rocket to reach its maximum height? And what is the maximum height? So we have this function h of t equals negative 16t squared plus v naught, that's our initial velocity. So right here, v naught is the initial velocity, v naught t plus h naught is the initial height, and we are given some information to fill in that v naught and h naught. We're launching from an 8-foot tall launching pad with an initial velocity of 104 feet per second. So this is what's substituted into h naught, and this is what's substituted into v naught. That's going to give us our function, negative 16t squared plus 104t plus 8. We read this question again. How long will it take for the rocket to reach the maximum height, and what is the maximum height? So this h that we have here represents the height. We notice here that our function for height is a quadratic function. So we want to find the max height. We notice height is a quadratic. We know the graph of a quadratic is a parabola. And we want to think about whether this parabola is opening up or down. We look at the value of a, that's negative 16. And because it's negative, we know that our parabola will be facing down. And that's really helpful for us because that means that we have a peak in the graph. We have a highest value, a maximum value. That max is going to occur at the vertex. So we can answer this question. We can find how long it takes to reach the maximum height, and we can actually find the maximum height by finding the vertex of this quadratic function. We have a formula for finding the vertex, and the formula for finding the vertex is negative b over 2a. That's the x-coordinate of the vertex. And then we have a y-coordinate, and the y-coordinate we can find by substituting the x into the function. So this should say negative b over 2a And this should say negative b over 2a. So in this example, a is equal to negative 16, b is 104, and c is equal to 8. And I just want to mention this over here because it can be kind of confusing that this h represents the x-coordinate of the vertex and not the height of the function. So let's calculate the h, which is the x of the vertex, and that's negative b over 2a, negative 104 over 2 times negative 16. Get our calculators for that. We have negative 104 divided by 2 times negative 16, and that gives 3.25. And I said that this is the x-coordinate of the vertex, but I misspoke a little bit because we're not using an x in our equation. We're using t. So this is really the t part of our vertex, representing time. So we have 3.25 seconds. So once we have the x part, the t part, then we can find the y part. So that's the h of 3.25. And I know this is confusing, but this h is the height. So we're going to substitute that 3.25 into the function. That's negative 16 times 3.25 squared plus 104 times 3.25 plus 8. We'll put that in the calculator. Make that a little smaller so I can see the equation. Negative 16 times 3.25 squared plus 104 times 3.25 plus 8. So we get 177. And this is going to be in feet on this example. Notice our velocity is in feet, our initial height is in feet. So this will be in feet. So this rocket will get a max height of 177 feet at 3.25 seconds. The price P and the quantity X sold of a small flat-screen television set obeys the demand equation below. How much should be charged for the television set if there are 90 television sets in stock? What quantity X will maximize the revenue? What is the maximum revenue? And what price should be charged in order to maximize the revenue? So in the first question, in the first part, it says how much should be charged for the television set if there are 90 television sets in stock. And we have this equation at the bottom with the variables P and X. Up here, it's stated that P stands for price, and X is the quantity sold. So when we're reading this question, it's saying how much should be charged. This is the price for the television set if there are 90 television sets sold. So this 90 refers to X, and how much should be charged is P. So we can use this equation to help us answer part A. This is called the demand equation. So P is equal to negative 0.15 times 90 plus 330. We'll use our calculator to work that out. We have negative 0.15 times, it should be times 90 plus 330. And the price that we charge for the television set should be $316.50. Now then in part B, it says what quantity will maximize the revenue and what is the maximum revenue. Now in this example, you don't see any variables labeled as revenue, so we're going to have to create this. Now luckily we do have a business formula that we can use, and the business formula is that revenue equals X times P. And the X and the P are the same X and P that were given to us earlier. So we're going to be able to build this revenue function. So we need to build the revenue function, X times P. It's going to be X times negative 0.15X plus 330. And I'll use a distributive property to get negative 0.15X squared plus 330X. So now that we have a revenue function, we can read this problem one more time. What quantity X will maximize the revenue? What is the maximum revenue? So those words about maximize and maximum are our clue that we're going to use the vertex. So just to back it up a little bit here, our revenue function, our revenue is a quadratic. The graph of a quadratic is going to be a parabola. Specifically for this example, A is attached to that squared term, which is negative 0.15. Because that's negative, we know that parabola is going to be down facing, and the maximum will occur at the vertex. Now we do have a formula for the vertex, and that vertex formula is that h is negative b over 2a, and k is f of negative b over 2a. Now in this example, we're not going to use f, we're going to use r for revenue, because we're dealing with the revenue function. So we need to find the vertex of our quadratic here. So h is negative b, that's negative 330, over 2 times a, negative 0.15. Now let's use that calculator. We have negative 330 over 2, let's use parentheses, 2 times negative 0.15. So we get 1100. And then K is the revenue at 1100 units. Negative 0.15 times 1100 squared plus 330 times 1100. We'll type that in the calculator as well. So we have 0.15, excuse me, that should be negative 0.15 times 1100 squared plus 330 times 1100. And we get 181,500. So we can finally answer part B, and in part B we can say that we will have a maximum revenue of the Y part, 181,500, by selling 1,100 TVs. We've got one more part here in part C. What price should be charged in order to maximize revenue? So remember, P, our price, is with this demand equation. So I'm going to take the 1,100. We need to sell 1,100 television sets to maximize the revenue. So the price that we should charge is negative 0.15 times 1,100 plus 330. That's negative 0.15 times 1,100 plus 330. And we get 165, so we should charge $165 if we want to maximize the revenue. Thank you for checking out my videos. Have a great day.